Hi everyone, welcome to the lecture on Introduction to Boosting. Today in particular we're going to talk about the adaboost algorithm. And this is the outline that I have for this video. We're going to review decision trees, talk about the boosting question, talk about ensemble of models, weighted decision stumps, and finally about the adaboost algorithm. So So at this point, I'm assuming that you guys took a class on a previous class in which you talk a lot about decision trees, but I'm going to introduce them just in case to refresh your ideas. So decision trees is a very popular machine learning algorithm. It's the building block from random forest and a lot of the gradient boosting algorithms. If a decision tree is not too bushy, let's say not too deep, it's interpretable, so you can understand what is happening. Then if you have a bushy tree is basically a tree that basically is very deep. We think about these trees as in general they tend to overfit. They have a high variance. High variance, remember, is the the model itself is sensitive to small changes on training data. Is low bias, so it fits well the data itself. So on the other hand, if you have kind of a very shallow tree, it usually underfits, so it doesn't fit well the training data, and it has high bias, so it doesn't so it doesn't fit the data as well. So let's recall what was this decision tree problem. So what you want is that you're gonna have to find. So in this case, for example, we have two variables x and y, and what you wanna do is that you wanna split the space. In this case, is this place the R2 space of these two variables. You wanna split them so that the circles get separated from the triangles, right? And the way we think about splitting those is that we split them with lines parallel to the axis. Okay, so we consider splits such that one of the variables is less than a particular value. So for example, or larger, right? So here in this example we have we split x into less than 0.43 or larger than 0.343, sorry. And then to the right, if x is less than 0.43, then we split y into less than 0.47. And to the left, sorry, to the right, for x bigger than 0.43, we split the y into less or larger than 0.33, right? And then after we have all the splits, basically what we do is that we look at the predictions. In this case is either circles or triangles, and we take the majority prediction. So in this case, the prediction is kind of perfect in a way. So we're able to divide triangles and circles perfectly. Now, in general, dividing, finding these best splits is an NP-hard problem. So actually, it's a very hard problem to solve exactly if you want to find the best split. So basically, what we do is that we solve this problem approximately. And how we do that, and I hope you guys remember this, is that we talk about splits that minimize impurity. So impurity is this mix of circles and triangles, right? So we want each a each basically decision tree to divide the space such that mostly we have either triangles or circles. So that it's more pure. Each split is more pure, right? So there are different measures of impurity, and these are some of them for the two-class classification problem. We can talk about misclassification error, Gini index, and entropy. And hopefully you guys saw this before. Today we are gonna just be simple and talk about misclassification error. Okay, so we're gonna simplify our life a little bit. So what is basically this tree fitting algorithm? It basically kind of looks like this. You look at each of your attributes, xj, okay, and each possible value that divides your train data, okay, and you split the data into two subsets, xj less or equal than a and xj bigger than a, such that basically you minimize impurity. And then you repeat these steps 1 and 2 in each subset. So you recursively split subsets, okay, until you basically have nodes that are pure or some kind of stopping condition is met, okay? Does it make sense? Okay, hopefully it makes sense. Okay, so this basically let's remind ourselves what is the simplest decision tree that we can have. And the simplest decision tree we can have is something called a stump. A stump is just a decision tree that just divides the data in two, basically. So for example, we have here that some data set, and we have either the income is bigger than 100K or smaller than 100K. And we just make decision or prediction just based on that, on one split. I am gonna start kind of throwing in some notation so that that we can kind of start talking about trees. And for example, in the case of stumps, we can write stumps kind of in this way, in which we have a variable xj, and we basically say, well, the variable xj can be bigger than alpha or smaller than alpha, and then we basically either give it a 1 or a -1. So we're talking about the case of binary classification, and we're going to instead of using 0, 1, we're going to use 1 and -1. And this is just going to become clear why it's kind of handy to use the 1 and -1 instead of the 0 and 1. Okay, so basically these are some possibilities on how to write these binary stumps. First of all, you have to consider which attribute we're going to split on, which value of the attribute you're going to split on, and what are the predictions we're going to give to each of the splits. Okay, I'm also having kind of a little notation, and I know that people have a little bit of problem with this notation here, so I'm going to try to explain it, and please ask me questions later offline. So what is a tree exactly, right? So basically a way to think about trees is that trees divide the space that you have. In this case is RD, so you have D variables, so the space that you have is RD, and the trees divide the space into disjoint regions that we're gonna call RJ, for J equal to 1 to a capital J, okay? And for these regions are like hyper rectangles in a way, right? So hypercubes or hyper rectangles. So they're kind of generalized version of rectangles, right? And for a point in a particular region, the value on that region is constant. Okay, so because what happens is that you divide the tree many times, you go to the leaves of the tree at the end, And at the end, in each of these partitions that we have, the value that we give to this prediction in these partitions is just one number. Okay, so a different way of kind of writing what a tree is that you take the indicator function. So the indicator function is the one function that we have here, 1 for x in Rj. This function is 1 in the region Rj and is 0 outside. So actually, let me write this down here. So when I write this function, let's kind of write it down here. So when I write this function 1, there are different ways to write it. So 1 on x in R, where R is a region. What is this? So this is the function that is like 1 for x in that region and is 0 if x is not in the region. Okay, sometimes I also write it like 1r like that, and this is the same. So this is 1 if x is in the region and 0 otherwise. Okay, makes sense. So basically what this function is saying here is that since all of these values of r are disjoint, what this is saying is that for x in a particular region, we're gonna have this function be beta j. Again, so this function t of x, what this is saying, t of x theta, is basically saying that this is gonna be beta 1 for x in R1 and beta 2 for x in R2, and so beta j for x in Rj. This is basically what this notation is talking about. Okay, and when I say theta are the parameters of this tree, what I'm talking about is that this tree is defined by all of these regions that we have that are going to split the space, and by all of the constants that are going to be the prediction that the model is giving on that particular region of the space. Okay, in principle, we want all of these regions to fill the space. So the union of all of the regions, R1, R2, Rj, they're going to be the whole space, which in this case is Rd, I guess. Okay, so if x, let me just kind of write down, x is in Rd. Okay, so we want the union of R1, Rj, for j equal 1 to big J to be the whole Rd. Okay, so please think about this a little bit. So this is just a notation, but we need those notations to be able to talk about not only this particular algorithm, but we're going to talk about gradient boosting in general, and we just going to need a bit more notation. Okay, so cool. So in this case, guys, what are the regions here, right? So let's think about them for a second. So for example, let's call R1 is gonna be like x less than 0.43, so that region intersect with y less than 0.47. So that is gonna be our R1. Then we have R2, could be maybe like So R1 is like basically corresponds to this part here, right? Then R2 is gonna be x less than 4.3 intersect with y bigger or equal than 0.47. Okay, so now I would like you guys to think about, so what is beta here? Okay, think maybe that, you know, circles corresponds to 1, and maybe these triangles corresponds to -1. So what is beta 1, beta 2? Okay, so sorry guys, I realized that I cannot write here. So let's write this R1 again. So what is R1? So R1 is, our region R1 is equal to x less than 0.43 intersect with y less than 4.43. Okay, so the question is, what is the beta 1 here? Then basically we have our 2 region here. What is beta 2, and so on. What is R3? What is beta 3? What is R4? What is beta 4? So that's basically something that I want you to stop the video and think about. Okay, so let's talk about what is this, about the boosting question, and let's basically give a little bit of more notation here. So we're given a training data, x1, y1, xn, yn, and we're assuming that, you know, y1, you know, yn, these are either 1 or -1. Okay, so it's a classification problem, and we are denoting our y as our target to be either -1 or 1, and also our predictions y hat I are gonna be either 1 or -1. So these are hard predictions, right? So this is the kind of the setting that we're gonna talk about today. So there is this notion of what is a weak classifier, you know. So a weak classifier has a few different properties. One is that it's fast to fit, so it's, you know, fast to fit. Second is that it doesn't overfit very well. It doesn't overfit basically, so it has like low variance. It actually tends to underfit. And has like a high bias. And it in general just doesn't have a great accuracy. Okay, so when we think about those, we can think about, for example, logistic regression with very simple features, shallow decision trees, or for example decision stumps. So these are basically potential kind of weak classifiers. So let's talk for a second about you know, about this idea of what is a learning curve, and you know, basically the relationship between classification error and the complexity of a classifier. So, and what happens in general, you know, what happens is that, you know, when we have a weak learner, meaning the complexity of our model is low, you know, what we have is that our training error, which is this curve here, and our, say, validation error or true error, they're both kind of high. Okay, and then as we increase the complexity of this model, what is going to happen is that since you increase the complexity of the model can fit better the training data. So the training error is going to go down, and at some point it's going to hit zero. In many cases it's going to hit zero, right? Because you increase the complexity of the model can kind of memorize the data pretty much, right? So the training error is going to go down, and at the beginning also the validation error is also going to go down, because maybe at the beginning you are kind of really underfitting the data, right? So you give it a little bit of more complexity, the model is going to fit better, right? But eventually, in many cases, what is going to happen is that the validation error is going to go up. So what we want in general is an algorithm that is kind of here, that is complex enough for this data. If we make it too complex, what happens is just gonna overfit, and our validation error is not gonna be as good, and we're not gonna generalize as well. Okay, this scenario happens with a lot of algorithms. It's not true just kind of in general. Deep learning breaks this plate a little bit sometimes, but this is in general true. Okay. So basically what we want in general is kind of this model that have kind of complexity in the middle, let's say. So how do we go from a kind of a weak model to more complex models, So, for example, if you have a linear model, you can add polynomial features, add more features. If you have, for example, one tree, you may want to have an ensemble of trees, kind of make an average of trees. And basically the question is here, is there any other way of going from this weak learner to a more complex learner? Okay, so that's kind of, we're gonna see that this is the question that adaboost is trying to, boosting in general is trying to answer, or the original question that was been trying to answer. So the boosting question is, can a set of weak learners be combined to create a strong learner? And again, a weak learner, think about just if you're talking about binary classification, it's just something that has just a little bit bigger than 50% accuracy, right? So it doesn't have to be very complicated. It doesn't have to be like it could be like a tree that is not very very deep, for example, right? By itself, that tree is not going to be very good. Yeah, can we combine a lot of these trees together and get a strong learner, right? So notice that, for example, when we talk about random forest, we want the trees to be really deep, in general deep, right? Because let's talk about that actually later in a different video. So I'm gonna talk about why you don't really want shallow trees when you are doing a random forest. So these trees are kind of different than the random forest trees in general. So let me briefly talk about ensemble of, even if most likely you guys have been looking at this before, but let's think about how do we get a prediction from, say, a bunch of different trees. So for example, here we have like 4 trees, and they give us, each of them give us a prediction. And how do we get just kind of how can we combine them, right? And one way that we combine them could be that each of one of these trees is gonna have basically a constant alpha 1, alpha 2, alpha 3, alpha 4, then it's gonna multiply them. So we're gonna take a weighted average of these trees. So how do we decide this alpha 1, alpha 2, alpha 3, alpha 4? That depends on different algorithms, and are gonna define these numbers differently. In the case of adaboost, we're gonna think about how good is the 3G1, how good is the 3G2, how good is the 3G3, and we're gonna define that alpha depending on a measure of how good those trees are. And then basically after we take this weighted average, okay, we're gonna take the sign of the sum of the predictions. So remember that this G1, G2, G3, G4 in the setting that we're talking about, their prediction is going to be +1 or -1. Okay? So it makes sense that at the end we just take the sign of this. So if there is more weight into the +1, right, we are going to get a +1 in our prediction. If there is most weight into the -1, we're going to get a -1 into our prediction. So okay, so basically this is the setting that we are in. So we have some kind of base learner. So the base learner is basically these weak algorithms, G1, G2, GM. Okay, so we have these M classifiers. Each of them gives an output of 1 and -1. Okay, and the prediction, what we do is that we take the weighted average using alpha 1, alpha 2, alpha m, which is also given by the algorithm. And then after we take the weighted average, we take the sign of that. And that is basically how we're going to predict. These are going to be hard predictions. So guys, I would like you to stop the video for a second and think about, for this particular example, what would be the prediction, right? So we have some input variables which are like income, credit, savings. So input is gonna be 120k, credit is bad, saving is 50k, the market conditions are good, and we have those trees that you have in there. And then we have this alpha 1, alpha 2, alpha 3, alpha 4 is how much weight we give to each of these trees. Okay, so my question is, what would be the prediction that this algorithm will give to this particular example or observation? Okay, so stop the video and try to understand how we do predictions here. So finally, after I have talked about different pieces, let me tell you about basically a pseudocode for the algorithm adaboost. Okay, so we're gonna have a training set x, y, yi. Okay, and we are going to initialize some weights, and at the beginning these weights are gonna be the same for everybody. So the weights are going to be 1 over n, okay, and they're going to be basically the same for everybody. Okay, so and then what we're going to do is that we're going to apply one of these base learners. It could be, for example, decision stump or a small decision tree to these weighted examples. Okay, and after we do that, we are going to increase the weight of misclassified examples. So if your tree misclassified a particular example, the next tree is going to give more weight to that example. Okay, so we're going to feed M trees. Okay, and then we're going to combine the models by weighting voting as we did before. Okay, so you guys may be asking yourself right now a question, right? How do we apply an algorithm to weighted examples? So we know how to work with unweighted problems. So how do we apply an algorithm to weighted examples? So suppose that you have two observations and one of them has weight 1 and the other one has weight 2. How do you guys think about that problem? Well, one possibility that I can think of is that if you have one example of weight 1 and a second example of weight 2, then one thing we can do is that we can put the second example twice, and then we have a new data set with 3 points. And that's a very good way to do this. Okay, We can more directly, we don't have to sample like this, but sampling is one way that we can do it. We can more directly think about the weighted problem um, in a slightly different way. So let's talk about that. So yeah, so before talking about that, I have some pictures here, and